So today, Benjamin, today on
What?
this episode of
Yes.
Science Actually Presents the Nerd and the Scientist, um,
Mm,
I figured the two main reasons that you love our conversations is because I'm Australian and I'm a scientist, right?
I do. That's the only reason I'm here.
That's it. I have no other benefit. So,
If you were Swiss, this would not happen.
well, I have good news then, mostly good news
Yes.
then, that we have joining us today another fantastic Australian astrophysicist, or as she likes to say, astrophysicist in prep, Rowina Nathan, who is joining us from Melbourne. She is also an astrophysics PhD candidate like myself, who works on all sorts of fascinating pulsar timing array science. Rowena, thank you so much for joining us.
Thank you so
Thank
much
you.
for having me. I hope the Australian accent is entertaining.
Yeah, it's very nice. I hope my accent entertains the both of you.
Yeah,
How
it's
about
good.
that? Right now, I'm doing the accent, actually.
Yeah, you are actually.
That's true. Yeah, I feel like he's not going to be able to understand half the stuff we say today. So,
We'll see how we go.
yeah, we'll see how we go.
Half stuff.
Yeah, but I was going over your website, which is a lovely website, by the way, in preparation for today's episode. And I mean, do you have one of those time turner things? Like, how are you managing to do all of this incredible science and outreach and teaching? And on Benjamin's Swiss comment, you were also like a ski instructor in the Swiss Alps at one point.
Yeah.
I saw that.
I don't know. I often feel like I'm not doing enough, so it's actually really nice to hear you say that, but that's classic academia imposter syndrome. I mean, I don't know if you remember from undergrad, but we get like 4 months off over the summer break, which happens to be Northern Hemisphere winter. So that's how I did the Swiss thing. And then, yeah, I think with the teaching and the outreach, it's something that actually really energizes me. And I feel like it makes my research go faster when I get back to it because it reminds me of why I do what I do and I can like take a bit of a step back. But yeah, sometimes it is a bit of a struggle to fit everything in.
No, that's really cool. And it's also relatable. Like, yeah, that imposter syndrome is strong. And I think that what's really great is, I don't know, I feel like the generation of mentors and faculty that we see right now, they're super in touch with that. And
Yeah.
they're always there to remind us. It's like, no, you are enough. It's fine. Take
I
a break.
always feel like I'm just pretending. And then my supervisor, who's a professor, will be like, me too. And I'm like, okay, so we all feel like that.
There you go.
Yeah.
Oh, wow. So, speaking of your research, would you like to tell us in a nutshell what it is that you work on?
Yeah, sure. So as you said earlier, I work on pulsar timing. So I'd say the main thing that I do my research on is pulsar timing and the gravitational wave background. So pulsars are little neutron stars that flash very regularly, and they flash so regularly we can use them to measure time very accurately. And because of that, we can use them to measure the gravitational wave background, which gravitational waves are tiny ripples in space-time. So they affect when the light from the pulsar arrives at the Earth. And by timing a whole bunch of them together across the galaxy, we can see really, really tiny ripples in space-time, which is the gravitational wave background.
Did you catch all that, Benjamin?
I did.
Cool. Well, that's the episode, folks. Thank you.
Thank you.
So I guess at this stage we have what, like 3,500 odd pulsars, right?
Yeah.
That we know about.
Mhm.
And so is the idea that your work is kind of looking at the signals that are detected, these like small offsets from their regular pulses,
Yeah.
and that's what's used to identify gravitational wave ripples?
Yeah, that's pretty much along the lines of what we do. There are about 3,000 odd known pulsars, but for pulsar timing, we only use the cream of the crop, the very best pulsars. And so I work for the Meerkat Pulsar Timing Array, which is a telescope based in South Africa, and we use only 83 pulsars, and that's actually the most of any of the timing arrays around the world. So it's quite a small data set, and even then, the best pulsars are the ones that like contribute the most information to what we're looking for. But yeah, we use specifically millisecond pulsars. So these ones rotate really, really rapidly, like hundreds of times per second. And then a lot of the pulsars, like you said, we have about 3,000, rotate slower than that, and then therefore they're not as good for timing.
Is that what makes it cream of the crop?
Yeah.
Pulsars?
Yeah,
The
so the
speed of it?
currency of pulsar timing is your average error on your timing solution. So we find a pulsar, we watch it for a while and see how often it flashes, and then we build a model that predicts when the next flash will come. And then the error on that decides how good your pulsar is. And our best pulsars are timed down to about a nanosecond. So crazy accurate.
Wow.
Yeah.
That is crazy accurate.
It is. I used to be able to say that pulsars were better at measuring time than atomic clocks, but then the atomic clock scientists got really good, and I can't say that.
They took it personally.
Yeah.
That's got to be the best grudge match ever.
Yeah. Who can measure time the best?
Wow. Okay, so I didn't realize it was only like 80. You said 83. Yeah.
83 for us. Yeah.
83 pulsars. Wow. And I guess, yeah, Benjamin, if it makes sense, like all of these pulsars are so regular and they never change how often they flash that, if they do, there's going to be some physical reason for it. And often, I guess what we see with gravitational waves is that the glitch, so to speak, in the pulsar, you see it across multiple pulsars, which shows that there's a gravitational wave that's passing through all of them. Did I get that right?
Yeah, that's right. So the pulsars are actually, there's a lot of things going on, right, that we have to model. So there's like dust in the galaxy between us and them that slows down the photons. There is the wind coming off the sun that slows down the photons. Even the gravitational well caused by Jupiter and the other solar system planets causes the photons to be slowed down because they get affected by the gravity from them. So we have to account for like so many tiny effects. And so there's always going to be a bit of noise, a bit of something going on that we can't explain. So the way that we know for sure it's a gravitational wave background is that it's correlated in different directions depending on where you look. So you're looking for a noise signal that, like, if they're opposite ends of the sky, it's anti-correlated, and if they're next to each other, it's correlated.
Mm-hmm.
Yeah.
I assume there's got to be a great many gravitational waves rippling through space in every conceivable direction. How
Yes.
can you, because it's everywhere, how
Yeah.
can you, with everything passing, I'm imagining ripples of water. If you throw two stones into the water at the same time, these ripples are going to hit each other, and then you very quickly lose track of where the waves are coming from. How
Yeah.
can you focus on one so you can see where one is coming from? Am I saying that wrong?
No, that's a great question. So you might know about the ground-based gravitational wave detectors in the US, LIGO, and they are for measuring like single events in a specific place in the sky. So you can imagine those like a loud explosion, whereas the gravitational wave background is the background noise of all the gravitational waves that ever happened for all of space and time. So
Right.
it's like a background hum. So we're not looking in any specific direction, but we're really lucky that gravitational waves, like, they have very specific polarizations according to general relativity, which allows us to look for correlations. Yeah.
The way that the wave is like flowing from like side to side or up and down, or
We can only have the cross or plus polarization, which I guess isn't important, but it leaves a very specific signal on our pulsars that we know to look for.
Okay.
I can see, for people just listening at home, I can see the cogs turning in Benjamin's mind. He's like, I guess that makes sense. Like he's getting it. It's working.
If we go back to the ocean analogy, I feel like the ground-based gravitational wave detectors measure tsunamis, just one-off like giant waves, and the gravitational wave background is like looking at like the waviness of the whole entire ocean at once.
Yeah,
Got it.
That's a good way of putting it. Nice. Wow. So I feel like sorry. I'm wondering, how did you find yourself in this part of astrophysics?
Yeah, great question, because when I started my PhD, I worked on like individual pulsar timing and looking at the most accurate way of detecting those flashes we can. So it's quite like, in my mind, it's on the other end of pulsar timing. On one end, you have looking at individual pulsars, and then on the other end, you have building a galaxy-sized array and looking for a background. But yeah, Meerkat is a new telescope, hence why it's so good, because it's brand new. And I just had an opportunity to join the pulsar timing array, and my supervisor used to work on creating maps for of gravitational waves when LIGO first became a thing. So he's very experienced in like mapping maths and things like that. And so it came time to start producing maps of the gravitational wave background using Meerkat. And since he's an expert, we worked on it together.
Cool.
Yeah. So I think it's probably a similar story to most astrophysicists. It kind of happens. It just happens. Like, you don't necessarily always have a vision of where you want to go. Your supervisor's like, this project looks awesome, and you're like, yeah, let's do it. So
there you go. See, it's thrust upon you.
Yeah.
You're going to be doing this because you just decided. Hey, this is neat.
It is
That's
neat.
all sciences. This is neat.
I mean, I think that's also what happened to me in a way, and you kind of just don't. You set out to do cool science because you think science is cool, especially space science, and then projects come along, and you're like, "Oh wow, yeah, that would be fun. That does sound like it's something I could do." And I think that's kind of the key point. Like, good supervisors know how to match those two things together, right? Where they can suggest a project that puts together your skills with something that's like relevant in the community and super interesting, and it's also feasible, right?
Yeah. I mean, that's why I guess in your PhD you have supervisors, because they know kind of off the top of their head which projects are going to work and which ones won't. But it's so funny when you start a new project, because like, sure, I know about pulsar timing, but there's a lot that I don't know. And you just kind of start turning up to meetings and just absorbing all this information, and everyone's talking, and you're like, I have no idea what anyone's saying right now. And then you just keep going until you have some idea of what's going on.
Yeah. I remember the seminars that we used to have during undergrad. There'd be these weekly astrophysics seminars, and my undergrad supervisor was like, just go to them and try to write down notes and absorb what you can. And I was like writing a bunch. I'm like, I know what some of these words mean, but like, what is going on? I think I went to him after one of the talks at the end of the semester, and I said, I maybe absorbed 20%. He said, that's fantastic. Next semester you'll get 30%. And that's kind of how you do it, right? You just
actually
keep building.
One of the ways I measure my growth as a scientist. How much I understood from the talks that I attend and the meetings I go to.
Nice. Yeah.
There you go.
I love that. That's also a way that you're not like comparing yourself to other people, which I think can often be an unhealthy approach, but you're just like, okay, how much do I understand this time? How much do I understand next time?
Yeah, 100%. In saying that, though, there was a time in my PhD when I was going to move to more LIGO science, so more those crashed bang kind of events rather than pulsar timing. But pulsars are just, in my opinion, the most magical objects in the universe, and I couldn't leave them behind. I really tried, but black holes, not for me. Pulsars, that's it.
Should we tell Benjamin about the nuclear pasta?
Yes. Oh my gosh.
Stop reading my notes. I swear to God, this is really getting me mad, dude.
All right.
Right there. Pasta and pulsars. Please tell me more. You stop it. Stop it. I'll send you a screenshot of my notes that you're just reading.
I swear I don't have access to your notes.
The Wikipedia page on nuclear pasta is probably my favorite Wikipedia page, closely followed by Axion quark nuggets, which also sound delicious.
We just did 2 episodes on quarks. How did we not come across that?
I don't know. I don't even know how I found it either, and I'm not like a particle physicist, so do I know what these things are? No idea. Just love the name.
Me either, but I like to eat things, so it just works.
Yeah. Nuclear pasta. I guess so. So neutron stars are insanely dense. They're only about 10 kilometers across, so that's smaller than Melbourne, but they're like way more than the sun. So they're the most dense objects apart from black holes. and they're the most dense objects that we can like get information from the inside of. And we have no idea how matter behaves at those kinds of densities, but basically the inside is so dense that it's smashed all the protons into the electrons, and you just have like hot neutron soup. And I'm not a particle physicist, so if you're listening to this and you're a particle physicist and you're like, that's wrong, I was going to say don't come for me, but feel free to. I would. Yeah, we don't know. Like, there's depending on the density and things like that. There's different structures that this quark gluon plasma, it's called, could form, and yeah, the shapes kind of resemble different kinds of pasta, and so that's what they were named by the scientists who decided to name them, which I love. And yeah, you can have sheets, so that's like lasagna, or like string-like things like spaghetti, or little blobs like gnocchi. My personal favorite nuclear pasta type of matter is anti-gnocchi because it makes me want to laugh.
What is anti-gnocchi?
Like a sponge.
Whoa.
It's like where the gnocchis should be. It's empty and it's in the, you know what I mean?
It's like a pasta donut?
Like hollow gnocchi.
Yeah, like anti-gnocchi. Where the gnocchi normally is, it's not there, it's in the other bit.
This astrophysics stuff is so easy. You see how fast I'm doing it?
You got it.
I love it. We should probably do a whole episode on astrophysics related food, but like not actual food, just things in astrophysics that are named after different foods.
Like
Cool.
spaghettification, which is completely
Spaghettification, yeah.
named.
I love it. Oh man. All right, Benjamin, I think you had an ad for us today, so we'll...
Yeah, let's do it.
Yeah.
It's perfect, and right after we're talking about food. Step right up, folks, and prepare to have your minds blown by the Gravi Toaster 3000, the world's first and only toaster powered by the cosmic magic of gravitational waves. That's right. This isn't your grandma's toaster. This bad boy harnesses the ripples in space-time to bring you toast that's universally perfect. Are you tired of boring old electricity? Let colliding black holes fuel your breakfast dreams. Whether it's lightly toasted or supernova level crunch, the Gravitoast 3000 gets it right every time. Don't get left behind in the dust of the cosmos. Join the gravitational revolution today. The Gravitational Toast 3000. Toast so good, it bends time.
That was strong. That
was good. That was good. I had a few arguments with ChatGPT to get it just right, but then I said, I'm writing it.
That was out of hand.
Oh, love that one.
So you said that's... Oh, sorry, go on.
The physicist in me the whole time was thinking about how to power a toaster with gravitational waves the entire time.
I think it would cook it very slowly.
Yeah, unless you like manage to find a pair of colliding black holes really nearby. But then you'd get one really crunchy piece of toast and then none.
I wonder how close the toast would have to be to the colliding black holes to toast it just right.
Yeah.
Have you seen that thing? How close do you have to have
the pizza radius
explosion? Or the pizza. How
pizza radius.
The pizza radius. How close do you have to have a pizza to whatever so that the heat cooks it just right? Same thing with toast and colliding black holes.
You can do the math on that, like the supernova shock waves, on the order of a few thousand kilometers per second, right?
Yeah, but this is slightly different because we're not powering it with electromagnetic emissions. It has to be gravitational waves, right? So the rate is probably different.
They would have to move something that generates the energy.
Yeah, so you got to have two black holes about to merge. Yeah, nice. I'm proud. That's good.
Perfect. We should copyright that immediatly. Yeah. I'm going to go and buy the IP address.
I'm not going to even air this thing about the toaster anymore.
No.
That's ours.
Gravitoast.com. Yeah, it's available. Buying it now. Cool.
Cool. Sweet.
So back to the actual gravitational wave science.
Yes.
So we are recording this episode in the last week of November, and we're going to release it in the first week of December at the same time that 3 papers are coming out about your gravitational wave science.
Yep.
So it's embargoed until then, but we got a sneak peek. Could
did.
you tell us a little bit about this work that you guys have done on mapping ripples in the cosmic ocean?
Yes, I certainly can. So, yeah, very exciting. On the 3rd of December, we're going to have 3 papers simultaneously released from the Meerkat Pulsar Timing Array, which is
Wow.
so exciting. And this is kind of a common practice in pulsar timing land. The different arrays will often release a series of papers together because there's so much analysis and so many steps to this work that you can't squeeze it all in one paper. And we have used the Meerkat radio telescope, which is almost pretty much the most sensitive radio telescope in the world right now. And it's really exciting because, well, the first thing is we've found further evidence for the gravitational wave background. And that was the first evidence was released last year in June by the kind of big players in pulsar timing. And they have 18 to 15 year data sets. So because the period of the gravitational waves in the gravitational wave background is so long, you need just a huge amount of data to measure it. But because Meerkat's so sensitive, we've found a similar level of evidence in only 4.5 years, which is a pretty big deal.
Wow.
So that's really exciting. And then on top of that, having the most pulsars and the highest sensitivity allows us to create the most detailed maps of the gravitational wave background. And in doing that, we had to come up with a lot of new methodology because we're so much more sensitive than before that the maths wasn't actually like equipped to deal with that. And in our maps, we found kind of what we expected, but also kind of not. So we expect the gravitational wave background to be the same in all directions, approximately kind of like the cosmic microwave background.
Mm-hmm.
And our maps are consistent with that, so that's promising. But one of the maps at the 7 nanohertz frequency has a little bright spot in the southern hemisphere, which we've been calling it a hotspot. And it's very intriguing. It's too early to say if it's real or not. It could be a noise fluctuation. It could be something else. But I personally am quite excited by it. And yeah, I guess it's a spot of higher gravitational wave power than the rest of the sky.
Wow. Okay, so when you say 7 nanohertz, you're talking about the frequency at which the gravitational wave is oscillating, right?
Yeah.
And so this one hotspot in the southern skies would indicate that there was a particular gravitational wave, like a tsunami, like you were saying, in reference to the LIGO stuff, coming from that direction. So what if it's not noise? What sorts of physical or astrophysical origins might it have?
Yeah. So for the gravitational wave background, those gravitational waves are made by supermassive black hole binaries. So LIGO events, the tsunamis, come from black holes like tens to hundreds of times the mass of the sun. We're talking millions to billions of times the mass of the sun. So the kind of black holes you find in the middle of galaxies, like our very own Sagittarius A star. But as we know, you can't just have one black hole to make gravitational waves. You need to have 2. And so this is 2 supermassive black holes orbiting each other. So the hotspot most likely would come from a supermassive black hole binary that's particularly loud in a galaxy that's relatively nearby compared to the other ones.
Mm-hmm.
And that could be interesting because depending on how big it is and where it is and things like that, it would challenge our current assumptions we make in cosmology, which is the study of the universe as a whole, which always pretty much assumes that the universe is homogeneous and isotropic. It's well mixed and the same in all directions. So if we have this one blaringly loud source that we can see in the background and the rest of it's looking pretty isotropic, that could potentially break those assumptions.
Mm-hmm. Wow, that's really interesting.
Yeah.
Could it be like a the upcoming merger of two supermassive black holes? Is that
So the physics of supermassive black holes orbiting each other is quite different from the lower mass black holes.
Mhm.
And the time for them to merge is almost the age of the universe. Like they
Mhm.
probably are never going to merge. And so that's helpful for us when we're doing maps because any sources we see, we can assume aren't changing in frequency because they change and evolve so slowly.
right?
So it's unlikely they're going to emerge. They're going to merge, but that's nice for us because from our point of view, they're pretty much constant.
So the black holes don't have to actually collide to make the ripples. They just have to get very close and just
Yeah,
create a lot of turbulence, I guess.
yeah, because these ones are so massive, but moving slowly, they can generate gravitational waves that we can measure without having an explosive merger.
Yeah, Benjamin's just mind blown.
And the
Well,
the orbital
there's one
period
place
is
where there's two super massive billions times the sun mass black holes making noise. Just one
Yeah.
place.
all the time.
Just one place.
Yeah. The period at which they orbit is 2 times the frequency. So for the bin we're looking in, it's about 4 years. So they're not like the smaller events where they're orbiting each other just before merger like hundreds of times a second. These are like
Mhm.
kind of gentle giants just rippling space-time.
That's funny.
Yeah, it's wild.
That's so
The
cool.
biggest things are taking the slowest time to
Yeah.
do these. That's funny.
Yeah, I guess the comparison in my mind is always to the chirp, right? To the gravitational wave event GW170817, where you basically see in the gravitational wave signature a kind of increasing pitch and frequency wobble that goes whoop 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 whoop,
Yeah.
and that kind of pop is the sound of them merging together. So this is kind of like that, but much more elongated.
Yeah. If we're talking sounds, another analogy I like to use, a gravitational wave from LIGO, from the smaller black holes, is like a pop or a bang or a crash. And the gravitational waves that we measure with pulsar timing arrays are like a background rumble or a hum.
Mm,
It's much lower in frequency and it's constant.
that's so cool.
No wonder she likes pulsars better than black holes.
Yeah. Oh my gosh.
If
And then
LIGO detects things that are nearby,
mm,
ish, relatively nearby, and pulsar timing arrays further away, where is that line? How far do you have to go before you switch from LIGO to pulsar timing?
that's a great question. LIGO can see pretty far away, like a lot further than we can see with light. Gravitational waves have a really fun physics thing where light spreads out with the radius squared, whereas we only have to deal with the radius, so we can see a lot further, which is very nice. And I know that with future gravitational wave detectors, we will be able to see to the Big Bang, so we'll be able to see everything, even in the LIGO spectrum. But the gravitational wave background, because it's a hum and it's a combination of signals from everywhere, we're also likely seeing back to the Big Bang. And it's currently a debate whether the majority of the signal comes from the supermassive black hole binaries like we were talking about, or from crazy shenanigans at the beginning of the universe during the Big Bang. So
The
like,
universe was young, shenanigans. It makes sense.
yeah, the young universe was hot, dense, crazy, and there was a lot
Yeah.
going on.
We've all been there. I have kind of a, maybe it's a dumb question. So like I know that with in terms of like electromagnetic cosmology, there's this dipole in the cosmic background that kind of shows the relative motion of our galaxy through the universe, right? Otherwise, once you subtract that, yes, the CMB is more or less isotropic in every direction. Is there a similar effect, like as we move towards, as our galaxy moves through the universe, we're kind of seeing a louder background hum in one direction versus another?
We aren't seeing that signal. And I actually have not even thought about why that doesn't happen in gravitational waves, but there's probably some fun physics that I'm missing. But we expect the gravitational wave signal to be quadrupolar. That's how we find it.
Mm-hmm.
And it seems to be pretty isotropic. So I don't know the
Okay.
answer to that question, and that's something I'm gonna have to look up. But I know that like generally in the field, that's what we expected, so we're not surprised.
Okay, that makes sense. Cool.
Yeah.
Yeah, I'm probably diving way too deep into the technical details. I'm sure that Benjamin has 800,000 questions. He's always much better prepared than I am.
I was swallowing water. Sorry. Apart from, I'm trying to rephrase this question because we kind of covered part of it.
Mm-hmm.
Other than all the different bits of interference, like gravity and dust bits and solar wind and everything, what other like technical or observational hurdles have there been in pulsar timing?
So I mean, up until now, we haven't had radio telescopes sensitive enough to have this many pulsars in an array. We used to have many less, but now we're able to find more and time more. But for timing, like I said, we only take very specific pulsars. All of the pulsars we use are inside the Milky Way galaxy for pulsar timing, which is handy because we don't have to worry about the expansion of the universe in that timing. But also, these are pulsars that the way that they spin so fast is they've been accelerated by a companion. So the companion can cause problems. Almost all of them are in a binary system, so we have to worry about the gravitational delay from the star that's orbiting them and things like that. There are so many things. Even if someone at the telescope trips over one of the wires, we have to account for that because it's going to change
Wow.
the solution. What else do we have to account for? And then pulsars, I mean, I've been telling you this whole time that they rotate extraordinarily regularly and we can use them to measure time. But each pulsar has its own little quirks, and sometimes they're just doing weird things, which is why we need a whole array of them. So we have to worry about those kind of events. We have our most sensitive pulsar, and everyone's favorite until it chucked a tantrum. Had this event, and we have no idea what it is. Most of the events that happen in pulsars were like, oh, that's a glitch, that's this, that's that. But this one, we're like, never seen anything like this, don't know what it is.
Is this Rami's pulsar?
That's Rami's pulsar.
Okay. Yeah, a good friend of ours, Rami Mandel, who is also astrophysics PhD candidate here in Sydney, has been spending a lot of his PhD trying to model and understand what this little tantrum was.
What is a pulsar tantrum?
It's flashing regularly and it's well behaved. The flashes come pretty much when we expect it, and then all of a sudden one day it's not doing that anymore and it's completely changed.
Okay.
We look
and
at
it
it
can
and
go
we're
back?
like, what?
And has it gone back?
Usually yes, sometimes no. The one we're talking about, J1713, everyone's favorite, seems to be settling back to how it was before. But because it was like our best, most consistent pulsar, it's really messing with things.
What are pulsar quirks? I'm sorry, we've heard it a couple of times this episode. What pulsars have quirks?
Yeah, some of
them are left-handed. I mean, what?
The more you get into pulsar timing, the more you get to know all the different pulsars, and they kind of become like friends. But each pulsar, when you look at the radio emission as like a line, how bright it is, their flashes are all different shapes. So they almost, I would consider their pulse profile, it's called, a little fingerprint of each pulsar. and some of them can be a bit wobbly. Some of them have like an interpulse where there's a pulse halfway between the main pulse every time, and they all have different shaped cones of emission. Sometimes they just turn off and we don't know why, like just nothing. But they usually come back on, so it's okay. I've been asked on my TikTok before if that's like aliens waiting until they're ripe enough to harvest them or something. I'm pretty sure that's not it, but yeah, there's always things going on, which is another reason why you want an array. If you have 83 of them, it's unlikely that all of them are going to have a tantrum at the same time.
Right. I mean, I guess the regularity is much so the regularity of their pulses comes from their rotation, right? The spinning about their axis, or at least the magnetic field is spinning about its axis, right?
Yeah.
And so that sort of thing is kind of hard to change on a dime.
Yeah.
But the thing that's actually producing the radio light that we see is this like dense cloud of plasma, an electron soup kind of thing that's interacting with that magnetic field. And that, I guess, is a lot more unstable, right? Is that a fair explanation?
Yeah. We don't fully understand how we get that radio emission from pulsars, but yeah, there's like this model of the beam where you can have, they call it a carousel model. So you have different regions of the star emitting that are going around. And yeah, the plasma and the stuff around the star, the crust that's generating the radio emission can be much more turbulent. And the regularity comes from the insane angular momentum of these objects. If they're that heavy and spinning that fast, you need just an insane amount of force to disturb it. And
Right.
so that's where a lot of the regularity comes from.
Yeah, I think we've maybe discussed in previous episodes the origin of neutron stars, right, Benjamin, where you have not on my show. What?
We've done so many.
Sorry, you're right. We should do fewer episodes. When
We're going backwards. We're going to study racing episodes. Please don't do that.
Yeah, you hear that, folks? Please listen to our first season before Benjamin deletes it. The whole angular momentum thing. So for folks who haven't heard our earlier episodes, and that I guess includes you, Benjamin, when you have a massive star that's more than 8 times the mass of the sun, that star, when it eventually runs out of nuclear fuel and it implodes and then explodes as a supernova, you basically have all of this angular momentum, right? So you had a big star that was slowly rotating. And then because of conservation of angular momentum, when the remains of that star compress down, the conservation of angular momentum means that angular movement leads to at a large scale, leads to a faster rotation at a small scale. So I think the example that people tend to give is of an ice skater, right? So if you have an ice skater with their hands or arms spread out, they rotate slowly, and if they bring their arms in, they rotate faster. So that's how neutron stars are born. Not through a stalk, through a massive explosion.
That was my favorite first year physics lab, was spinning around on spinny chairs with our arms out and our arms.
I know, right? I was about to do it.
Yeah, that's a funny thing about neutron stars is we often say that they're dead stars, which is a weird way of thinking about it. Also because neutron stars can die. So then, I don't know how you make an analogy with the life cycle of a living being when something can die twice, but there you go. Maybe it's like a live star, zombie star, dead star or something.
I think, yeah. Maybe I've been watching too much Buffy recently, but yeah, I think you can kill something that's dead, I guess, somehow. If it's a zombie, sure.
Yeah.
There you go. Yeah.
But it's funny that's the majority of things that we study in radio astronomy tend to be dead things.
Same in gravitational wave astronomy, and there's this beautiful plot that's been made of all the gravitational wave events we've measured with LIGO and the mass of the two objects that merged and then their final mass. And the title of the plot is The Stellar Graveyard.
Mm-hmm.
So just looking at dead stars Those are the only things heavy enough to make gravitational waves that we can measure.
I mean, it's a really cool plot. I think Aaron Geller was the one who made that plot, from Aaron Geller from Sierra Northwestern. I think that was one of the visualizations he came up with. But yeah, it's funny also in the world of pulsars and neutron stars. There's this diagram that shows like the period of their rotation versus the change in their period. So it's called a P dot diagram. P dot being the change in P, the change in the period. And there's this kind of line drawn across that diagram showing another graveyard. So like within this phase space where all of the dead neutron stars live, there's a graveyard where the dead ones allegedly don't go. Until recently, we've been finding a few that kind of toe the line into that stellar graveyard. So
pulsars are so pesky. We come up with a rule and we're like, okay, this is how they behave. We've looked at a pretty big population and that's how we feel. And then we keep looking and then they're not behaving the way that we expect.
I mean, it's kind of like with supernovae, right? We're like, okay, cool. So we figured it out. There are type 1 and type 2 supernovae. This is it. These are the rules. And then nature says no. And then you end up with a whole bunch of subclasses. But this is fun. This is how science works, right? We come up with theories, we try to model things, and we realize the universe is complicated. It's got quirks.
Our theories were always right. There'd be no space for you or I to do a PhD because we would have worked everything out already.
Yeah. And people were saying that at the turn of the 20th century, right? They were saying like physics is solved.
Yeah. No.
Done. Next.
Speaking of next, what is next for you? What is the next project that you're thinking of working on after these 3 papers get published?
Yeah, great question. I am currently working on a project which is super statistics heavy, because all of the maps that we've produced for this set of 3 papers have a lot of assumptions baked into them. And like I said, we've been able to relax some of them because our radio telescope's so sensitive and things like that. But we want to be able to relax more of them to kind of remove as many assumptions as we can so we can see the universe as it truly is rather than how we think it should be. And so that's what I'm working on at the moment, which is arguably much less exciting because the maps are probably going to look almost the same as they do now to the naked eye, but it's important to get things right. And then after that, I'm not too sure. Hopefully working on some more pulsar timing array things. I think we'll find out if this hotspot is real soon enough when we start to combine data from all of the pulsar timing arrays around the world and as we continue to observe and measure that data. So I hope to continue working on mapping and hopefully seeing what the universe looks like in gravitational waves. The resolution of this spot, the amount of space it takes up on the sky is also way too large for us to even begin to hypothesize which galaxy this signal could be coming from. So hopefully observing more pulsars and increasing the resolution and better understanding what this thing could be.
That's so awesome.
Yeah,
I said awesome first.
Also, hopefully finishing my PhD and becoming a doctor.
Yay! Yeah, sweet. Always a good goal.
That sounds awesome.
Yeah.
I think, Benjamin, did you have any other questions? I feel like we've covered all of gravitational wave ripples and
I think cover everything. I got every little thing that's possible. Pasta and pulsars, got that.
And I swear I didn't have access to your notes.
One of my favorite, I'll just add a little tidbit that you can edit out or not edit out. So I love measuring scales in fun units. And so the gravitational waves we measure with LIGO, with the ground-based detector made of lasers, the laser arms are 4 kilometers long, and the gravitational waves change that length by less than the width of a proton. So that's crazy that we're accurate enough to measure that.
That's another question on his list, I reckon.
Okay. No, it's another note right there. Let's see. There. If LIGO detecting movement the scale the fraction of a diameter of a proton.
Yes. So when we're using a galactic scale detector, which is what our pulsar timing array is, the gravitational waves perturb. If we had a laser the length of the galaxy, it would change the length by the width of a 2x4 Lego brick.
Sorry. One more time. That just blew my mind.
Yeah. The gravitational waves change the length of space-time in the galaxy by less than the width of a Lego brick.
Oh my god.
Which Lego bricks is a really great unit of measurement, I think.
You have no idea how
Love
much
it.
I love Lego. You don't see it. I'm surrounded by Legos at the moment. I'm so very happy right now.
Yeah. And I think it's insanely cool that we can measure that. Like, that is so tiny, and yet here we are.
I love it.
Galactic Legos.
Galactic Legos. Yes, we should start a campaign for Lego, see if we can get 10,000 people to support a galactic scale pulsar timing array Lego set.
Can you imagine that? Could you
I would
imagine
buy that in
that?
a heartbeat.
I'd buy it in a millisecond. Oh, well, this has been amazing. Thank you so much for joining us and for taking the time. Where can people find you on the internet if they want to?
Thank you so much for having me. It's shameless self-plug time. You can find me on TikTok and Instagram. I'm at Pink Astrophysicist. That's pink, the color, astrophysicist. I love getting questions in my Instagram comments and TikTok comments. So please ask away, and I might make a video and respond to you and explain what's going on. And that's where I'll also be doing a bunch of explainer videos about this research that's coming out. We've covered it pretty well here, but if you want to learn more, listen again, you can find me there.
Amazing.
Pink Astrophysicist.
Yeah.
Pink Astrophysicist.
I'm not
Fantastic.
well enough today. I got pink glasses, but I'm not wearing pink.
I mean, that's, yeah. For folks who are just listening and not watching, you are missing out on my hot pink, or is it fuchsia? Hot pink astrophysicist T-shirt that says "Gravity" in Barbie font. So, yeah, and which Benjamin made.
Thank you. It's one of my favorite ones to make. I'm sorry.
Fantastic. Benjamin, where can the good people find you on the interwebs?
Please look me up under the name Science Actually on Facebook. That's the big one. But of course, I'm on all the time wasters, Twitter and Instagram and Threads and Mastodon and Hive and LinkedIn and blah, 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 blah. But please, how about you, Kovi? Where are you?
You can find me in all the good places and also the bad ones at Fun Fact Science. I've been noticing things popping off more on Blue Sky recently.
Yes.
Oh, that's the other one. Yes. People are making a lot of jumps to Blue Sky lately.
Mm-hmm. Mm-hmm. Yeah. No, it's great. I think Blue Sky has overtaken Threads. So, yeah, definitely hop on. Give us all a follow on those platforms. I mean, if you're hearing this, you're already listening to the episode at least. But if you want to see our beautiful faces, you can check us out on YouTube or TikTok. And we will see you next time on the next episode of Science